So let's have the part 2 of our lecture video in Geotechnical Engineering with the topic Lateral Earth Pressure. Let's continue solving examples number 3 to 5. Okay, so we have here number 3, a frictionless vertical retaining wall has a height of 6 meters. The backfill is sloping at an angle of 10 degrees from the horizontal. The unit weight of soil is 16 kN per cubic meter with an angle of internal friction of 20 degrees. The soil is cohesionless. First, compute the Rankine active pressure coefficient. Second, compute the Rankine active force on the retaining wall. And then the third requirement is compute the moment due to this active force. So in this example, we are considering a sloping backfill. So the drawing for this or the figure for this is like this. The backfill is sloping at an angle of 10 degrees. Okay. So first one is compute the Rankine active pressure coefficient. So we have formula for a sloping backfill from our study guide. So we have here with inclined backfill, and we are solving for active pressure coefficient. So this is the formula. So the formula for Rankine active coefficient is K sub A. For letter A, we have K sub A is equal to cosine of alpha minus square root of cosine alpha squared minus cosine of phi squared. Over cosine of alpha plus square root of cosine alpha squared minus cosine phi squared. Right. So we have here from our figure, alpha is the inclination of the backfill, and we have given here the phi or the angle of internal friction. So we just substitute all of them into the formula. So we have here cosine of alpha, which is 10. That is cosine 10 minus square root of cosine 10 squared minus cosine of 20 squared all over cosine 10, okay, plus square root of cosine 10 squared minus cosine 20 squared. So K active is now equal to 0.5312. So this is K active. Next, we are to find the Rankine active force on the retaining wall. So what are the involved here? So we don't have cohesion. Cohesion is 0. There is no surcharge. We have here soil. So how do we treat or analyze if we have a sloping backfill? So here we are consider the soil, and we are taking it horizontally like this. Why? Well, the top of our uniformly varying is at the top of the structure. So although we have a sloping backfill, we are still focused on the height of the structure. So that's why our uniformly varying load for soil here, okay, so this is for soil, is starting from the top of the structure. Okay, so let's get the force. But how about the force? How do we treat the force here? Now, since the inclination, the backfill is inclined, the force, it is the force which is inclined. So here is the force. Okay. So the inclination of the force is also 10 degrees. This is F. Okay. So how do we solve for the force now? For letter B. Now for soil, to get the value of pressure for soil, we have K active times the unit weight of the soil times the height. K active is 0.5312. The unit weight is 16 and the height is 6. That is equal to 51 kilopascal. Now if we get the value for P, we now have the value for F. And that is from the uniformly varying here, we have 1/2 base times height. So 1/2, the pressure is 51 and the height is 6. And that is equal to 153 kilonewton, and that is in per meter width. Okay, so that is for Rankine active force on the retaining wall. How about letter C? Compute the moment due to this active force. Now, we know that moment is the summation or it's the force times the distance. Now, where does the structure rotate? So, we know that the structure will rotate here at the heel. Therefore, the distance will come from the bottom of the structure up to the force. So, how do we treat the moment for the force here? We will take the value for f of x. We get the value for f of x. We now have here, okay, so find the distance y from the bottom to the f of x, okay, or the component of the force. So that's how we will be able to find the value for moment. So let's get the value of f of x. F of x is f cosine of 10, and that is 153 cosine of 10, and that is equal to 150.68 kilonewton. And the distance y is 1/3 of the height, and that is equal to 2 meters. Therefore, we now have the moment, okay, the active moment there as f of x times y, that is equal to 150.68 multiplied with 2. Therefore, m sub a is now equal to 301.36 kilonewton meter. Okay, so that's for the moment due to the active force. Okay, so screenshot first before we proceed to the next example, number 4. Right, so let's go to number 4. Okay, so we have here a 3 meters high. So the figure is actually given. We have a 3 meter high vertical retaining wall shown. Question is, what is the effective vertical stress at the base of the wall? So vertical effective stress, we're looking for P sub E, which we discussed from the previous topics. Next, what is the total active force on the wall? FA total. Okay. And then letter C, what is the total active moment on the wall? Okay, first, let's solve for the P sub E. Okay. How do we solve for P sub E again? Okay, so from the top, let's start from the top. We have gamma of 15.7. So that is equal to 15.7 times the height of that particular section, that is 2. Plus, we have the gamma sat. Okay, so we have here a water table, and then we have gamma sat. Since we are computing for P effective, therefore, we deduct water from the gamma sat, 9.81, and then the height of that section. Therefore, P sub E is now equal to, so P effective is now equal to 40.49 kilopascal. Next, what is the total active force on the wall? So let's have all the components here. So do we have cohesion? None. None for the section above. We don't have cohesion there. Then we have cohesion here. What do we observe also? We need to take note that these are two different soils. So phi here is different from the phi on the lower section here, the lower part. Okay? So again, let's be reminded, we will be applying the special case here for the soil part. Now let's refresh that. We discussed that special case in the part 1 of this topic. Okay, so first and foremost, we need to have the K active. Solve for K active first. Okay, for letter B. Let's put here letter B. K active 1. So 1 minus sine of phi all over 1 plus sine of phi. That is equal to 1 minus sine 30 all over 1 plus sine of 30. Okay, that is equal to 1/3. Now let's go to K A sub 2. 1 minus sine of 26 all over 1 plus sine of 26. That is equal to 0.39. Right, so let's start with the cohesion. There's no cohesion at the top. Okay, so this is water table. So there is no cohesion, but we have here cohesion at the bottom. So we have here cohesion. And the orientation for cohesion is, the tendency is to push the structure towards the soil mass. Okay, so this is P sub C, and we are going to treat this negatively. Okay, so we have there P sub C. And we don't have any surcharge. Yes, we don't have any surcharge. So we only have here P cohesion equals, the formula for cohesion is 2C square root of K active 2, because it's located below. So 2 times 2, the cohesion, okay, yeah. Cohesion is 2 kilopascal. Then square root of K active 0.39. That is now equal to 2.5 kilopascal. After cohesion, we don't have surcharge. Let's go to the soil. For soil, okay, so let's draw here. That is uniformly varying. Then let's get the value for P sub 1. So for P sub 1, for soil, we have K active 1, gamma 1, H1. So our K active 1 is 1/3. Our gamma 1, what's our gamma 1? Gamma 1 is 15.7. Height 1 is 2 meters. Okay, so we have here 15.7 and then height of 2 meters. And that is equal to 10.47 kilopascal. Now let's go to the next one here, the special case. Since they have different phi here, phi 1, and then this one is phi 2. Therefore, we have a special case. Let's have a different color for that. Or, okay, so our special case will be the P sub 2. Let's compute first. Why special case? So P2, we have K active 2, but we're using gamma 1, H1. So the gamma of the soil above and the height of the soil above. So 0.39 for Ka sub 2, 15.7 times 2. And that is 12.25 kilopascal. So this is bigger or greater than P1. Therefore, if we draw that here, so this is our so it has here P sub 2. So that's P sub 2. Then let's get the P sub 3. The uniformly varying of the lower soil. This is P sub 3. Okay. So that's for the soil. So P sub 3 is Ka2, K active 2, gamma 2, H2. So 0.39 times our gamma buoyant is gamma sat minus the gamma of water. So gamma buoyant is gamma sat is 18.9. So we have here 18.9 minus the water, then the height of the lower part. So we now have here 3.545 kilopascal. Next, we have the water. Okay, for water, it's also uniformly varying. Okay, let's put it here. So let's put it P water. That is equal to gamma water H2. So 9.81 times 1. So this is 9.81 kilopascal. Okay, so let's go now to the forces. Since we are solving for the total forces, this is FC. This is F1. Okay, so let's name this as F1. Then this is F2. And then this is F3. And this is F water. Okay, so let's solve for force cohesion. Force cohesion is simply PC times 1. Okay, so that is equal to uniformly distributed, so it's an area of the rectangle. So we have here PC H sub 2, PC is 2.5, H2 is 1, therefore FC is 2.5 kilonewton. Then F1 is uniformly varying, and it's a triangle. So we have there 1/2 P1 H1. So we have there 1/2 P1 is 10.47, H1 is 2. That is equal to 10.47 kilonewton. F2, the special case a while ago, this one here, it's rectangular, so it's just P2 times height. So P2 H2, P2 is 12.25 times 1, so that is 12.25 kilonewton. F3 is uniformly varying, it's 1/2 P3 times height. P3 times the height, H2. So 1/2, our P3 is 3.545 times the height is 1. So F3 is now equal to 1.77 kilonewton. Then we have there F of water. F of water is uniformly varying rectangle, triangle. So 1/2 PW times height. So 1/2 PW times the height, H2. So 1/2 and then PW times the height. That is 4.905 kilonewton. Okay? Since we're going to summation of forces is equal to 0. And then we have here positive to the left. Okay. Positive to the left, therefore F total for active force is negative FC plus F1 plus F2 plus F3 plus FW. So you just simply add all this. That is equal to negative 2.5, positive 10.47, plus 12.25, plus 1.77, plus 4.905. So FA is now equal to 26.9 kilonewton. So that's for the total active force. Now letter C, what's our letter C? What is the total active moment on the wall? Now to get the moment, we need the values for the distance of the forces from the bottom of the structure. So let's put this here. So we need the values for YC, so Y1, Y2, Y3, and then the YW. So we need the values for the distances. Alright, so for letter C, we have YC. We know that it's a uniformly distributed load, so that is 1/2 of 1, so 0.5 meters. Y sub 1, Y sub 1 is 1 plus 2/3 of, or 1/3 for 2. Okay, so that is 1 plus 1/3 of 2. So 1 plus 1/3 of 2. Next, Y sub 2. Now, Y sub 2 is this one here. It's just 1 divided by 2. So Y1 is 5/3. Next, Y sub 3. Y sub 3 is 1/3 of 1 meters, and the same is true with Y water. Okay, so Y3 is equal to Y water is equal to 1/3 m. Okay, next we have summation of moment. A is now summation of moment at point 0 is equal to 0, point of origin. So we have their positive, counterclockwise. So if this is our rotational point, so this is our rotating point. Therefore, we now have here MA is equal to negative FC YC plus positive F1 Y1 plus F2 Y2 plus F3 Y3 plus F water Y water. That is equal to negative 2.5, 0.5 plus 10.47, 5/3 plus F3 is 12.25, 0.5 plus 1.77, 1/3 plus 4.905, 1/3. Okay, total moment now is 24.55 kilonewton meter. Okay, so that's for number 3. Number 4. Yeah. Now let's go to the example number 5, and this is our last example for this topic and in this video also. So analysis. So analyze the stability of the frictionless wall shown. So when we say analyze, so we need to determine whether the structure is stable in terms of both forces and the moment. So how do we know if the structure is stable or not? Well, we have discussed about, or we have tackled about the passive and active forces. So in terms of forces, if the ratio of the force is, say, force passive over force active is greater than 1, what does it mean? Now, we discussed that the forces in passive tends to make the structure stable, whereas the force active will tend to push the structure, so it will cause instability. So if the force passive is greater than force active, then the structure is stable. Or that if we take the ratio will be greater than 1, that is stable. Same is true for the moment. If the passive moment is greater than the active moment, or the ratio of the passive moment over the active moment is greater than 1, therefore the structure is stable. Now, for this whole structure to be stable, we must satisfy both these criteria. In force and in moment, it should be stable. But if one of them is not stable, there is a needed adjustment either for the height of the structure or the height of the backfill. So it depends. You need to do some necessary adjustments just to get this done, or just to get a stable computation. Okay, so let's start with so this is the structure, so let's have a look. So the structure here is in the middle. It has a backfill to the right, so it's encountering a backfill to the right, and that backfill is encountering surcharge of 20 kilopascal. This backfill on the right is 2 meters with gamma of 19 kilonewton per cubic meter, and the angle of internal friction 25 degrees. And then there is a water table here, and from the bottom of the structure to the water table we have 4 meters. Gamma sat now is 20. Phi, or the angle of internal friction, becomes 30 degrees. And then on the left side, the backfill for the left side, the soil that tends to stabilize the structure here, we have gamma sat because it's experiencing also here the effect of water. So there's water table on the left side. So 20 kilonewton per cubic meter, and angle of internal friction for 30 degrees. Okay, so meaning this is the same soil. Okay, so let's start first with so this side here, the right side, are the active pressures. So it's experiencing, or this structure is experiencing active pressures on the right, and then on the left we have the passive pressures. Okay. Okay, let's see. Let's compute. Start with the right side. Let's start with the active pressures. Let's write here active. So these are the active pressure. So we don't have cohesion. We have surcharge, soil, and water only. Okay, before we proceed, let's have the active pressure coefficient, K sub A1. That is 1 minus sine of 25 all over 1 plus sine 25, that is equal to 0.406. And then we have K active 2, 1 minus sine of 30 all over 1 plus sine of 30, that is equal to 1/3. Okay, let's start with the surcharge. Okay, let's position it here. So this is the surcharge part. Let's find the value for P sub 1. Oops. Alright, so P sub 1 is equal to K active 1, then surcharge. So let's write here surcharge. So K active 0.406 times the surcharge is 20. It is equal to 8.12 kilopascal. Next, let's find P sub 2. Surcharge again, K sub A2 Q, 1/3 of 20, that is equal to 6.67 kilopascal. This one is greater than this, therefore we now have the diagram to be looking like this. Now this is now our P sub 2. Then we have soil. And for our soil, we have another special case because of the different angle of internal friction for the upper and the lower section here. So the uniformly varying for F sub 3. Okay. So let's have a uniformly varying here. This is P sub 3. So for P sub 3, we have K active 1, gamma 1, H 1. So K active 1 is 0.406, gamma 1 is 19, height is 2. Let's see. Yeah, 19 and 2. That is equal to 15.428 kilopascal. Let's go to the special case, P sub 4. So P sub 4 is K active 2nd, but we're using the one above. Okay. And the reason is they have different phi. Okay. We have there 1/3. Gamma 1 is 19, H1 is 2. That is 12.67 kilopascal. This is greater than this. Therefore, our drawing for here will be so this is the P sub 4. Therefore, the uniformly varying for P sub 5 for the soil, the lower portion, will be something like this. sub 5. Okay, so P sub 5 is K active 2 gamma 2 H2. This is 1/3, and our gamma 2 is gamma buoyant, 20 minus water. So gamma sat minus gamma of water. So we have there 20 minus 9.81. The height again, that is 4. That is equal to 13.59 kilopascal. Lastly, we have the water. So this is for the water. Okay. So water, PW. So P water is equal to gamma of water H2, 9.81 times 4. That is equal to 39.24 kilopascal. Now let's get all the forces. So this is F1, F2, F1, F2, this is F3, F4, F5, then F water. Okay, so we have for F1 and F2, it's just the area of a rectangle. Same with F4. F4 is area of the rectangle, P4 times the height. F3, F5, and FW is area of the triangle. So I will just do quick writing here. So F1 is P1 H1 is equal to 8.12 times 2 is equal to 16.24 kilonewton. F2 is P2 H2. So you can always refer to the diagram on how I'm getting all this computation. Then for the F3, that is triangular, so 1/2 P3 H of 1, so 1/2 P3 is 15.428. Our H1 is 2. So this is 15.428 kilonewton. F4, the special case, that is a rectangular, P4 H2, and that is 12.67 times 4 is 50.68 kilonewton. Then we have the F5. F5 is triangular, 1/2 P5 H2. That is 1/2 P5 is 13.59 times the height of the lower portion, the 4, 27.18 kilonewton. Then lastly, we have the F of water, that is triangular, 1/2 P of water times H2. So 1/2 P of water is 39.24 times 4. That is equal to 78.48 kilonewton. Now, the total now for these forces, F active is now equal to F1. So, summation of forces positive to the left, we have F1 plus F2 plus F3 plus F4 plus F5 plus F of water. That is equal to 16.24 plus 26.68 plus 15.428 plus 50.68 plus 27.18 plus 78.48, and F active now is equal to 214.69 kilonewton. Okay, let's box this because we need this for our ratio later. So finally, we get one parameter here because we are solving for FP, FA, MP, and E. Just to test whether it is greater than 1 or not. Okay? Now, after we get the value for force active, we need the moment, the active moment. And to get the value for active moment, we need the distances of the forces from the bottom. Okay. So we need the values for y1, we have y2, so y3, y4, y5, and then we have the yw. For y1, that is 4 plus half of 2. For y2, we have 4 plus, that is 4 divided by 2. For y3, we have 4 plus 1/3 of 2. For y4, we have the 4 divided by 2. And then we have y5 as 1/3 of 4. Same with y water. Okay, so let's write that all here. y1 is 4 plus 1/2 of 2. That is equal to 5 meters. y2 is 4 divided by 2, and that is 2 meters. y sub 3 is equal to 4 plus 1/3 of 2, and that is equal to 14 over 3 meters. Y sub 4 is equal to 4 divided by 2, that is 2 meters. Then we have y sub 5 is the same with y sub water, or yw, that is 1/3 of 4. Therefore, we now have moment active equals F1 y1, F2 y2, F3 y3, F4 y4, F5 y5, plus F water y water. That is equal to 16.24 times 5 plus 26.68 times 2 plus 15.428 times 4/3, 14. Yeah, 14 over 3 plus 50.68 times 2 plus 27.18 times 4/3 plus 78.48 times 4/3. So MA, moment active, is now equal to 448.797 kilonewton meter. Okay, now we have the force active and the moment active. Okay. Next, we go to the passive side. The passive side is the left side of the structure that we have here. So here it is. So this is the passive side. Let's compute that one. So for passive pressure, let's have the K passive, or the coefficient for passive. So P here is 30 degrees. For K passive, we have 1 plus sine 30 all over 1 minus sine 30, that is equal to 3. Okay. Now, what we have here, so there is no cohesion, there's no surcharge. What we have is the soil uniformly varying. And the water also uniformly varying. Okay, because of the presence of the water table. Alright, so this is for soil. Oops. So this is for soil and this is for water. We need the value for P1, then P water. So for P sub 1, we have there K passive gamma 1 H1 or gamma H. So 3 times gamma buoyant. So we have here gamma sat 20, therefore we're going to get gamma buoyant 20 minus 9.81. We remove the water. The height here is 4. So 122.28 kilopascal. Next we have P water. P water is gamma water times height 9.81 times 4. And that is equal to 39.24 kilopascal. Then let's compute for the forces. So we have here force 1 and then force 2, force water. For force 1, we have there 1/2 base times height. So we have there 1/2 base is 122.28. The height here is 4. So 244.56 kilonewton. Force water is 1/2 P water height. So 1/2 P water is 39.24 times 4. That is equal to 78.48 kilonewton. So for total passive force, we now have F1 plus Fw. F1 being 244.56 plus 78.48. So Fp is now equal to 323.04 kilonewton. Then for the moment, we have the value for Y1 and Y water as equal. So Y1 is equal to Y water is Y water. It's equal to 1/3 of 4. 4/3. Therefore, the moment, passive moment, is now equal to F1 Y1 plus F water Y water. It is equal to F1 of 244.56 times 4/3 plus 78.48 times 4/3. So M passive is now equal to 430.72 kilonewton meter. Now here is the moment of truth. Let's see if the structure is stable or not. So let's find the ratio of forces. The ratio of forces, F passive over F active. Now F passive is 323.04 divided by F active. Active forces is 214.69. So 214.69, the answer here is 1.505. This is greater than 1. So this is okay. That means it is stable. Right? Nice. Now let's check for the ratio of moment. So we need to have stable for moment just to say that the structure is stable. MP, MA. So MP is 430. 430.72 divided by MA. MA here is 448.797. That is 448.797, and that is 0.96. This is less than 1. This is not okay. Unstable. Unstable because when we're talking about the moment of the the active portion is greater than the passive portion. We passed on the forces, but we failed with the moment. Okay? So why? Why is that? It means we can adjust in terms of, when we are talking about moment, of course, we are multiplying force times the distance. So in order to make the passive moment greater, okay, so to make it greater, let's go to the main figure. That means we can adjust the height of this side of this structure. We can increase the height of the soil on the left side just to make it stable in terms of the moment. Okay, so if you increase this side, if you increase the height of this, you again solve and see if it is again stable, right? So that's how we analyze this wall. So that's all for the example number 5. So screenshot. Here's the passive pressure. Okay, so all in all, the structure is unstable. But you can rectify, you can increase the recommendation is to increase the height on the soil at the left side. Okay, so that's all for this part 2 video.